The consequences of climate change are being witnessed around the world, floods to droughts to heat waves. And to combat the consequences of climate crisis, our next report looks at a $1.3 million Oyster reef project.
Florida dumped 500,000 tons of discarded oyster shells offshore, expecting little more than an experimental restoration project. Instead, those restaurant leftovers transformed a barren seafloor into a thriving underwater ecosystem.
Thousands of tiny mollusks have begun growing on the artificial reefs dropped in the bay as part of a plan to mitigate damage in far south. They are made from a mixture of cement, sand, and crushed oyster shells, a crucial ingredient that attracts living oysters to make their home here.
Oysters multiplied, fish returned, and turtles and dolphins began appearing around the growing reefs. But the transformation didn't stop there. The reefs filtered polluted water, restored seagrass habitats, and even protected coastlines from powerful storms. What started as a controversial pile of waste became one of marine science's most surprising success stories. How did these discarded shells trigger such a dramatic ecological comeback? The bold experiment. Between 2007 and 2024, Florida wildlife officials launched a bold coastal restoration experiment near Cedar Key. Discarded oyster shells were collected from restaurants and processing plants, loaded onto barges, and deposited across the Gulf seafloor. In total, more than 500,000 tons of shells were used. The project immediately faced strong opposition. Environmental groups called it ocean dumping disguised as conservation, warning that the shells could bury marine organisms living in the soft sand. Commercial fishermen also feared the deposits would disrupt sediment, damage fishing grounds, and permanently alter the coastal ecosystem they depended on. Despite the criticism, officials continued. Their reasoning was simple. The shells were already destined for landfills, and reusing them might help rebuild damaged oyster reefs. The potential benefits were significant, but even project leaders expected recovery to be slow and uncertain. 18 months after the first shells were deposited, monitoring teams returned expecting to find little progress, or evidence that the critics had been right. Instead, they discovered something remarkable. Marine organisms were rapidly colonizing the shell mounds at rates rarely documented before. The shells were not behaving like lifeless waste. They were providing stable surfaces where oysters, microorganisms, and other marine species could attach, grow, and reproduce. What began as a controversial dumping project had triggered a surprisingly fast ecological transformation, challenging long-held scientific expectations about how quickly damaged marine habitats could recover. Scientists like Dr. Krimsky, a shellfish habitat specialist for the Commission, were honestly pretty startled because these routine debriefings got cut off right in the middle of a sentence. Not from, scheduling, but from the sheer size of the discovery. The seafloor was waking up faster than anyone imagined, and what had been treated like waste was suddenly doing something else entirely, acting like a seed for a growing, breathing system. It wasn't merely reef construction, not at all. This felt more like an ecological comeback happening on a timeline that people had sort of brushed aside as unrealistic. Also, it did not seem to move slowly over the years in a calm, predictable way. It looked like it happened quickly and densely, reshaping that flat, featureless seafloor into a habitat that was suddenly complex. The whole thing caught researchers and the surrounding community off guard. Everyone had to pause and basically reconsider the basic assumptions about how reefs form and how quickly restoration could realistically proceed. Before long, it became obvious the outcome wasn't only shell piling, it was nature taking back space with a kind of stubborn energy that was hard to ignore. Still, the actual engine, the real driver behind the change, stayed out of view at first glance. Even people who know this area well understood that the initial colonizers, small microorganisms too small to see without instruments, were going to matter a lot. What formed beneath the surface was, frankly, stranger and more layered than anyone predicted. That hidden sequence looked like a necessary stepping stone, a key step toward figuring out how the reef would eventually take shape. Those early, slightly shocking findings then set things up for a deeper dive into the way microscopic life and chemistry work together. The result was a rebuilding ecosystem that would soon impress outsiders and quietly win over believers too. The mystery of how life took root so rapidly on discarded shells reveals just how far off expectations were. Invisible beginnings. The first life to colonize the dumped oyster shells was not fish, nor shells, nor any visible marine creature. It was bacteria. Within days of the shells settling on the seafloor, microscopic bacterial communities began spreading across the calcium carbonate surfaces, creating thin biofilms. These biofilms weren't a random scatter but organized living carpets, turning inert shells into functional microhabitats essential for what came next. These bacterial films served as biological infrastructure, laying a foundational living layer that future marine organisms would build upon. Oyster shells themselves played a chemical role beyond physical structure. Composed mainly of aragonite, a crystalline form of calcium carbonate that slowly dissolves in seawater, the shells released calcium ions into the surrounding water. This caused tiny localized alkaline zones, microscopic chemical environments within the broader Gulf seawater chemistry. These microzones were crucial because they provided exactly the right chemical conditions for calcifying organisms like barnacles, tube worms, and juvenile oysters to attach and begin growing. The shells were essentially manufacturing a chemical handshake that invited colonization. This meant the shells were not just physical litter but active participants shaping their own biological fate. Weeks following biofilm establishment, diatoms and microalgae moved in, feeding on the bacterial mats and laying the base for a rudimentary but vital food web. These primary producers sustained microscopic crustaceans and larval mollusks, which in turn attracted the first juvenile fish. The ecosystem's early stages formed a self-reinforcing cycle, all growing out of what began as discarded seafood scraps on a previously lifeless seafloor. This transformation really mattered, in a kind of profound way, because sandy seabeds, the stuff sitting under most of Florida's Gulf floor, basically can't do much in terms of physical and chemical nuance for biofilm to take hold and for reefs to actually develop. Sand doesn't provide a dependable surface, no real chemical gradients, and not much of any habitat structure. It just stays, well, sand. So the Gulf bottom ended up in a biological dead end for decades, stuck there, unable to bounce back to reef life unless something came from the outside to interrupt the pattern. The dumped shells sidestepped that dead end entirely. They gave a physical framework and also the chemical hints that life seems to respond to. Within 6 months, biofilm and microalgae took over the shell surfaces, and suddenly those once lifeless piles looked like a completely different scene, at least to the sensors and microscopic viewpoints still watching from below. That invisible step, full of bacteria, chemistry, and tiny grazers, was the real scaffolding that helped complex marine life return later on. Water samples plus sediment cores backed up what was happening. They showed that a working microscopic community formed faster than what traditional artificial reef efforts often manage, biologically speaking. Without the bacterial biofilms, the chemical makeovers, and that earliest little food web, the shells would have just been calcium laid out on sand, irrelevant and unused by marine species. In other words, the groundwork for reef growth was already there, but unseen and still indispensable. And from that invisible base, the whole system was able to push toward a notable ecological comeback. It even started to reframe what scientists had assumed was possible, stretching the boundaries of restoration science and giving fresh clues about reef formation right at its earliest stages, where most of it is happening out of view. From this microscopic awakening, the next chapter revealed how ancient reef builders returned to a Gulf once thought incapable of renewal. Oyster rebirth. Oysters need hard surfaces to survive, but that requirement had become a major problem along Florida's Gulf Coast. Oyster larvae, known as spat, drift through the water until they find a solid place to attach. In healthy reefs, they settle on layers of old oyster shells built up over generations. Those reefs once supported hundreds of marine species, filtered coastal waters, and protected shorelines from erosion. But decades of overharvesting, pollution, runoff, and habitat destruction had broken down much of Florida's natural oyster reef system. By the early 2000s, large areas of the Gulf floor had become soft sand, leaving young oysters with almost nowhere to settle. The discarded oyster shells deposited near Cedar Key changed everything. The shell mounds created concentrated hard surfaces directly in the path of drifting larvae. Within the first year, researchers found juvenile oysters attaching to the shells in numbers far higher than expected. By the second year, many of those oysters had matured and begun reproducing. Their larvae settled on the growing reef, extending it beyond the original shell piles. Human intervention had created the starting point, but nature quickly took control. By the third year, surveys recorded an average of about 847 oysters per cubic meter on the deposited shells. Nearby sandy areas without shells supported almost none. The reefs also began expanding both upward and outward. As older oysters died, their shells remained behind, creating new surfaces for future generations. This formed a self-sustaining cycle in which the reef continued building itself naturally. What began as loose piles of restaurant waste soon became complex living reefs filled with marine life. The project showed that damaged coastal ecosystems may recover much faster than expected when the right conditions are restored. Sometimes, rebuilding an entire ecosystem does not require complicated technology. It only requires giving nature the foundation it has been missing, one discarded shell at a time. As oyster reefs were re-established, they set the stage for an explosion of marine biodiversity and ecological complexity that no one had fully predicted. The rebirth of oysters marked just the beginning, as life cascading upwards would reveal the full scale of nature's comeback. Exploding life and diversity. As the oyster reefs took shape, the scale and speed of life returning to the seafloor astonished researchers and locals alike. Within 2 years of the shells being deposited, fish biomass around the reef sites increased by more than 340% compared to nearby areas without substrate. Species diversity rose by nearly 280%, marking not just a larger number of fish, but a far more varied marine community flourishing on this new habitat. This wasn't just fish relocating, it was a surge of juvenile fish born and raised in these waters, signaling true ecosystem regeneration. Redfish were among the first to appear, using the complex shell structure for feeding and shelter from predators. Following them, sheepshead fish thrived, feeding on invertebrate communities established on every hard surface. Flounder patrolled the reef edges, while snook made appearances in numbers never before seen in these waters for many years. The reefs were no longer barren patches on the Gulf floor, but vibrant hotspots of marine life jumping back to existence. The volume and diversity of marine life attracted the attention of fishermen who had once opposed the shell dumping. Charter captains who had testified against the program witnessed firsthand a remarkable change, with fish stacking up thickly around reef mounds. Captain Mike Lenz, a vocal early skeptic, famously changed his tune after seeing schools of redfish holding steady in the currents, admitting he'd never seen anything like it in over 2 decades. This convergence between lived experience and scientific data marked a turning point in public perception. Past the fish, the reefs kinda held this flourishing invertebrate scene. Octopuses took up real estate in the reef's gaps and overhangs, using the messy structures to both prowl and stay out of sight. Sort of. Sea turtles came back too, grazing on the invertebrates that clung around shell surfaces. And yeah, even dolphins showed up, hunting in a smart way along the reef edges, doing coordinated sweeps through thick fish clusters. With all these returnees stacked on top of each other, the whole system got more layered and also more steady, tightening food web ties from the seabed upward. What made this marine comeback feel extra meaningful wasn't just that life relocated. It was more like they were creating fresh life altogether. A lot of older artificial reef efforts mostly pull in the fish that are already around, almost like a magnet, but they don't really raise the total ocean numbers. These oyster reefs, on the other hand, built a kind of nursery habitat where juvenile fish could survive better. And that survival translated into biomass that wasn't really there before. In other words, it became a big ecological win for Florida's restoration work. Meanwhile, hotels, bait shops, and those waterfront restaurants in the area were seeing real upticks in revenue tied back to stronger marine activity near the reefs. That economic ripple was basically proof that the reefs were becoming more important to nearby communities that depend on both tourism and fisheries. Over time, the people who once opposed the project started leaning the other direction, and some were even asking for extra reef sites from the commission they had sued in the first place, which is kind of wild. And as the reefs kept driving a wider burst of fish and invertebrate variety, they were turning into true keystone habitats, holding steady an array of species that had been gone for years. Then, as the revival got faster and more obvious, the environment began shifting in ways that weren't only about animal counts or whether fishing improved. Life return was rewriting the Gulf's story. But beneath the surface, another transformation was quietly reshaping the water itself and promising far-reaching consequences. Ecosystem cascades. The restored oyster reefs in Cedar Key became giant natural water filters. A single adult oyster can filter between 30 and 50 gallons of seawater each day, removing excess nutrients, harmful bacteria, and pollutants. With hundreds of thousands of oysters spread across the reefs, billions of gallons of water were naturally cleaned every day, without electricity, machinery, or ongoing maintenance. This filtration helped tackle one of the Gulf Coast's biggest environmental problems: nutrient pollution from farms and cities. As water quality improved, harmful algal blooms declined, oxygen levels increased, and the water became much clearer. Sunlight could once again reach the seafloor, allowing seagrass beds to return after years of decline. The recovery of seagrass created another wave of benefits. It provided a nursery habitat for juvenile fish, manatees, and sea turtles while stabilizing sediments and keeping the water even clearer. Together, oyster reefs and seagrass formed a self-sustaining cycle that boosted biodiversity, strengthened coastal ecosystems, and delivered ecological services worth tens of millions of dollars, all at no cost to taxpayers. The project's success inspired similar restoration efforts across Alabama, Mississippi, Louisiana, and even New York Harbor through the Billion Oyster Project. Researchers and engineers in Canada, Australia, and Europe also began studying Cedar Key's approach as a model for restoring damaged coastlines. The reefs also proved their value during Hurricane Irma in 2017. Shorelines protected by oyster reefs suffered about 30 to 40% less erosion than nearby unprotected beaches. Their rough, three-dimensional structure absorbed wave energy before it reached the shore, preventing an estimated $3 million in property damage during a single storm. Unlike seawalls, oyster reefs repair themselves naturally as new oysters settle after storms. By improving water quality, restoring habitats, and protecting coastlines, these living reefs have become a powerful example of how nature can rebuild and defend itself for generations. The growing reefs and thriving marine life were rewriting not just the Gulf's ecological future, but also the way people think about restoration, resilience, and the power of nature's quiet comebacks. Coastal protection and legacy. By the early 2020s, Cedar Key's restored oyster reefs had expanded far beyond their original size without further human intervention. Each new generation of oysters settled on the shells of older ones, steadily building larger, more complex reefs. Over time, these living structures formed crevices, overhangs, and sheltered spaces that became home to crabs, octopuses, sea stars, and juvenile fish. What began as piles of discarded shells evolved into thriving ecosystems with biodiversity similar to natural reefs. The reefs also give this kind of surprise climate perk. As oysters get bigger, they tuck away carbon in their shells and also in the nearby sediments, which ends up lowering greenhouse gases while the water quality gets better too. And it's not only about marine life, but there's this broader ecological weight to it, like a living method for coastal resilience, sort of quietly doing its work. Their biggest test showed up with Hurricane Irma in 2017. The shorelines that had those restored reefs took on about 30 to 40% less erosion than places right next to them that weren't protected. The reefs kind of soaked up the wave energy before it really reached the coast, so the storm's raw damage power was muted, even if only by a lot. Engineers figured they spared around $3 million in property damage during just that one hurricane, which is a strong payoff for a restoration effort that cost roughly $5 million spread across 15 years. And unlike typical seawalls, oyster reefs can mend themselves after storms. New larvae settle, and they keep building, so the reef continues, not just sits there. That means it becomes a long-term, budget-friendly strategy for coastlines that are vulnerable, while still backing marine ecosystems at the same time. Right now, endangered sea turtles have returned. Dolphins cruise and hunt near the reef edges, and the fish count keeps improving. The Gulf is rebuilding itself in a way around these living reefs, and it's pretty clear that nature can bring back things that were once lost. 500,000 tons of used oyster shells became the basis for this ongoing environmental success narrative, shielding coastlines and supporting wildlife for future generations. Florida's oyster shell project transformed discarded waste into a thriving, self-sustaining reef system that restored marine life, improved water quality, and protected vulnerable shorelines from powerful storms. It proves how quickly nature can recover when given the right support. If this incredible transformation inspired you, please like and subscribe for more stories about small actions creating extraordinary change. And before you go, continue the journey by watching the next video appearing on your screen. Thanks for watching.